Some people are online.
Few people are online.
How much time do you think you
I will take 1 hour plus 15 minutes. It has some hands-on also. 15 minutes of hands-on
keep it all within 1 hour?
within 1 hour. Okay, try to do that. Try to. So for 1 hour we have to start now.
Yes, go ahead.
Yeah.
طبعا
It's about 5 minutes.
Dr. Salam very much for his contribution and يعني he volunteered actually to give the first when I asked some other faculty at Anthroplasty, he said I will start. I will launch the seminar series. Okay, we have the seminar series inshallah, and this one
I haven't received such invitation.
yeah. Oh really?
Yeah.
Okay.
I think
You have the seat. But you will get it inside the
for a seminar invitation from you.
yeah.
If you want to cut down, you can next week we do. And you're at it.
No, I will check it. I will check it. So Dr. Salam is يعني thankfully will give the seminar about the finite element methods in research, and teaching maybe and so on. And thank you very much for his efforts. Go ahead.
Just want to make sure that in the online attendees, my voice is audible. Anyone can comment on this? Online attendees, my voice is audible. I hope it is audible, I think.
Yes, we can hear you. Yes, thank you.
Okay. I think the online attendees, are my voice audible?
Yes, yes, it is.
Just want to confirm, although it is, I think it is audible. Actually, I don't have my phone also. Can you check via phone?
Good to enter voice.
I think you have to connect the white wire.
They can
The
hear.
white,
Is it?
yes, the white one. But still,
I think our voice should be audible.
We cannot hear you.
I don't know.
yes,
Ask the they can hear.
Am I audible?
Yeah. Let's ask.
Afsar. Oh,
Yeah.
actually, I was audible and people were responding, but my voice was actually off.
But now it's okay.
It's okay now. So without wasting time, we will start and we'll try to finish within 1 hour. So everybody knows about, first of all, good afternoon, everyone. Thank you for attending. And we will discuss a few important terminologies related to finite element method. And we will start with the few basics. And we will also see in which field a finite element method are now being days used extensively. As you can see in this simple figure, a finite element method itself actually gives you a clear picture of the important critical areas defined during a flight. So a thrust generated by the engines and the area around it are the critical and the important areas. So just by representing a proper coloring method in a rainbow fashion, a finite element method is very expressible in itself. It gives you a clear indication to a layman also that these are the important and the critical areas, and the material around them will be of important choice. We will divide this session in two parts. In one part, we will discuss about the importance of finite element method in various fields of engineering. Secondly, we will try to do a 10 to 15 minutes hands-on in which we will see how to build a simple model on a finite element tool. So first of all, we will discuss few problems, very basic problems which are there in engineering. This is a simple tension test. This test, a simple dog bone specimen which has a gauge area, and during a loading, the gauge area is exposed to high stresses. These stresses are represented by a simple finite element model. In other application of bending, which is related to the civil engineering, a 3-point bend test is done in most of the classes of problem where the material properties are to be obtained. This is a simple 3-point bend test where this part is fixed, this part is fixed, and the load is applied from the top. This will obtain a bending and flexural stiffness of the material. So usually this is an experimental procedure. Through the finite element method, people have tried to simulate it and obtain a matching material properties corresponding to the experimental counterpart. This is one problem related to the manufacturing, where a chip formation is observed during a machine. The important thing to note is that though there is a chip formation, the tool is also deformable. Chip as a material is a deformable for sure. Here the tool is also deformable. That's why it can see various stresses acting on it. Though the machining process is a very complex process, and obtaining such type of a finite element model is a very complex in nature, because the elements are getting deleted at each and every section. It's a highly non-linear complex problem. No, not multiphysics. Yes, thermal concepts are also included in finite element method, and we will discuss that.
If you make the grid all domain or the grid only about the part that moves.
No, this
There is a grid that will do.
Yes. This material is getting feed. This is a feed part. This material is getting feed. The tool is fixed, and the material is being feeded through the tool.
No, I talk about the mesh.
Hmm.
The mesh for the whole domain or just the extended IRS intensity?
The mesh,
The mesh only this on the color region, or also the other has a mesh, but you cannot see.
in this one or the other regions here? One, two, three.
My question is that now this is moving up.
Mhm.
This move, there is mesh here.
No,
We cannot see.
No, no.
This means the mesh is moving.
no, no. This is a movement of the material. This is a dynamic problem, movement of the material. This movement is created when the tool,
Okay, it's
Tool is
movement
fixed.
of the material.
yes, movement of the
At the
material.
beginning was the problem.
Yes,
Did you make use all this block as a mesh?
no,
And then the movement inside
no,
the mesh?
no.
Okay, this mesh is moved.
Yes, yes. This is moving in this direction. Just this is a dynamic situation, just like happens while machining a material.
And the mesh can move in any place, any area.
It will move according to the physics of the problem.
The mesh moves based
Yes.
on the physics.
Physics of the problem.
That
yes.
you just at the beginning do the first slide. Yeah. Right? No. Yeah. That's only stop. This,
Sorry.
this only the stop. This only the mesh.
Yes,
And then by running, the mesh is moving.
yes. Then
And the
the
number also increase?
no mesh number. No,
No.
No.
This means that the mesh size is expanded.
no. The mesh is fixed. We will discuss about the mesh also. The mesh is fixed. Once the mesh is fixed, it is fixed. After that, this is the physics of the problem through which the cutting, this is the chip of the material. So chip is coming out as the physics is moving. So this is through the physics of the problem.
What about the mesh?
Mesh is Mesh
The
is-
shape can move. The shape can move.
In fluid mechanics, we do the mesh
No,
for
no,
all
no,
domain.
no,
For
no.
example, in this case, I will through a cup of water. In this case, should make all the room mesh. Then inside the mesh, the water can move.
No.
That we all solve for all the domain. But this is my question: is this all the domain? You solve
No,
all the domain,
no.
and
This
the
is
body
not the-
move here, or this is just the mesh, and you solve only in this area?
Only in
and
this
then
area.
expand-
Only in this area.
Only in this
Only
area.
in this area.
And in this case, if this area increase,
Hmm.
the number of mesh increase,
No. No.
the size of the mesh decrease.
No. It is constant before the
But
problem.
how, doctor, it should be the number increase or the size change? How we cannot, we can see the expansion. How the mesh cannot expand?
Mesh is fixed. For the solid problems, the mesh is fixed.
Mesh is fixed. How is moving up?
This is due to the physics of the problem. This is due to the physics of the problem, the mesh is moving. Huh. Can we move?
Yeah.
In this case, this is FEM in military ballistics. So this is the impact of the projectile on plate. Although this is a composite plate made up of many layers. And these composite plates, as you can see, these are the various stresses experienced during the impact, a projectile impact. Now, we can see various field variables like failure in the shear direction, failure in the ductile phase, failure of the matrix, failure of the composites, etc. We can also see the delamination part, and we're going to see that. So through the FEM, we can actually cut the section and see the details of the inside layers, how the layers gets their delamination during the failure. So in experiments, this is very difficult to observe. The inside delamination that you can see of various layers. So this is one of the major advantages FEM gives you. In biomechanics, there's this field FEM is also being expanded in biomechanics and related medicine area, where this is one of the papers of ankle anthroplasty, which is a replacement of the joint. So you can see that the contact pressure is generated at these areas, and these areas is the first peak. This is an intact ankle, and this is ankle anthroplasty. That means uh, a prosthesis ankle. And this is a mid stance. As the pressure is increased, this is simulated, and externally the contact pressure is increasing. This is for the further increase in the pressure. So FEM is actually utilized in various fields, of engineering. Now we'll see how it solves wide variety of problems in engineering. Now, any approach, any physical phenomenon can be modeled either as a continuous approach or as a discrete approach. In a continuous approach, as you can see, this child is sitting on this stool. So we can model this. The child can be modeled as a lumped mass with a center of gravity, CG, and this stool can be modeled as a shell elements. And we will discuss about the shell elements as well. So all the degrees of freedom can be approached using a simple discrete mathematical approach. So we'll use the same approach in FEM to build the models. Now, the question again remains that how FEM solve wide variety of problems, the application areas that we have seen. This is mainly due to the common feature in the mathematical formulation, because many engineering problems can be represented by a same differential equation. That means in many cases, the differential equations are same. Like for example, a Poisson's equation or Laplace equation, they all represents a heat flow, maybe a torsion of bar, groundwater seepage problem, etc. How the solution happens is another important area. So first of all, in any problem, we have a governing differential equation, which is always accompanied with the boundary conditions. So a governing differential equation and a boundary conditions we have. So what we used to do, we used to assume a trial solution, a simple trial solution, a linear trial solution is assumed. Like we need to find out the displacement at this point, ux, xy maybe. So let's keep it one dimensional. So ux is a simple polynomial function like a1, a0 plus a1 x plus a2 x square plus a3 x cube and so on. So this is a simple polynomial which can increase its order, and as and when it increases its order, it can capture various deformations that can occur on a model. Once this equation is there, this equation needs to be satisfied with a boundary condition. In FEM, this is known as natural boundary condition. So this simple trial solution satisfies the boundary condition, and then the equation that obtained is then used to solve the governing differential equation. The overall idea is to minimize the error. So once the error is minimized, we finally end up with the forces times stiffness times displacement. Because any problem or any element in these finite element meshes, it depends upon two field variables, force and displacement. The stiffness is the material property, which is the K. So each and every element has its force component, and a displacement component, and they are related with a K matrix, which is a stiffness matrix. How it is done? Now, to understand that, it is important to understand the concept of degree of freedom. It's very simple. Minimum number of parameters required to define a position of a point. Like for example, at this point, we have 2 degrees of freedom. It can move in X and Y direction. This point has 3 degrees of freedom. It can move in X and Y directions, and also this line can rotate. Sorry, this line can rotate. In this one, this is a 3-dimensional aspect in which the point can move in 2D and it can rotate in 3 directions. So each and every point has 6 degrees of freedom. Here, the degrees of freedom are 3. Here, the degrees of freedom are 2. Here, 3 at each node. Here, 6 at each node, because 3 transitional and 3 rotational. So the same concept we'll be going to use to discretize our problem. So discretization or meshing is a very important phenomenon in finite element method. So what does an FEM does? FEM reduces the infinite degrees of freedom to a finite order. Like this is a problem domain. We know that a continuum material made up of many particles. So there will be an infinite number of particles. So an infinite number of particles can be reduced to a finite number of particles by using and joining these nodes. These are known as nodes of the element. So here the number of points are infinite, but here the nodes are finite because we have finitely reduced our domain. Although in a 3-dimensional, 6 degrees of freedom at each node. So total number of equations are finite again. This is how we discretize or breaks down our problem in simpler parts, solve each part, combine together and makes a overall solution. Now these elements may be rectangular or may be triangular. There are nowadays polyhedral shapes are also there. So let's talk about the element types. So usually for 1-dimensional cases, we have a simple beam 2D element. If it is a beam, it can have 2 directions, X and Y. Along with it, it can rotate also in 2D plane. It has 3 degrees of freedom at each node. We have 3 nodes also. In this case, the procedure will remain the same. Then to represent and solve 2D problems, a 2D elements like a triangular, 4-noded quadrilateral, or maybe a 6-noded triangular nodes can be used. As and when we are increasing the nodes, we are increasing the degrees of freedom. And further, we are increasing the overall equations. If you remember the last one, as and when we are increasing the number of nodes, degrees of freedoms are increased. Degrees of freedom remains the constant, but as and when the nodes are increasing, the overall equations are getting increased. So you can increase the node to obtain the more accurate solution, but the overall computational resources will be much higher. And something very similar goes to 3D, because in 3D, all 6 faces has to be there. So the nodes increases in size. And these increase in size actually makes the problem more and more complex. So this is the reason why the computers are being introduced to solve these complex problems using finite element method. Now, we know that these nodes are the building blocks of any problem, and all the calculation happens at these nodes. Calculation means that the displacement is obtained at these nodes, and using the displacement we can obtain the stresses, strains, etc. So at these particular nodes, the field variables are there: stresses, strains, displacement, etc. But what about inside the element? Inside the element, the information is not available because nodes are not present. If you put a node anywhere, it will give you an information of displacement, stresses, and strain. But in the inside of the element, the nodes are not there. So the FEM interpolates the results. It extends the results using simple shape functions. So the FEM calculates the results at nodes only, but these results are extended at unknown or any required points inside the element. These are known as shape functions. The shape functions are represented as, so U1, a displacement at this node, U2, maybe the displacement at this node. Similarly goes for these two also. So the overall displacement inside the element will be N1 U1 plus N2 U2 plus N3 U3 and N4 U3. Where these N1, N2, N3, N4 are the shape functions which represents the interpolation of the results over the element. Now to understand this more, we will go back to any of the problems that we have seen. Like in this one. If I can zoom this, I don't know. Yes. Now these are the elements. Everybody knows these are the small rectangles are the elements. We know that these have 4 nodes, 1, 2, 3, 4, or here you can see 1, 2, 3, 4 nodes they have. But about the deformation, they have the information inside the element also. These deformation information inside the element are produced by shape functions, which are linear simple interpolation functions, which used to give the deformation over whole of the element. Otherwise, we would have got the deformation only in the nodes. So the shape functions connect themselves from one element to another, and they gives a progressive deformation profile over the surface. Now, what about the accuracy? The accuracy of the FEM depends upon one's choice, how much accurate solution he wants in its results. So, like for example, this is a simple circle. If we shade it with a triangle, so this much part is left out. If you make it with 4 lines, the rest of the part is much smaller. If you make it with 6 lines, the rest of the part or the remaining part becomes even further smaller. So as and when we are increasing the nodes, our solution is increasing, our accuracy is increasing further. In this graph, this is clearly shown that as and when the number of nodes or lines are increasing, the exact answer, let's say, is 100. This is going and having a curvature onto this. And for most accurate, you can see that it is having a displacement of about same as what it is. So an increase in the number of elements or nodes will lead to a higher accuracy. A small advanced part of the FEM that we're going to see today is the solver that is used to solve the problems. Any problem can be defined in 2 general aspects. Either it may be a static problem or it may be a dynamic problem. In the static problems, we may be having a linear analysis or a non-linear analysis. In the linear analysis, the Newton's first law governs every problem, which represents summation of all the forces equal to 0. That means there is no acceleration in the problem. For the case of non-linear analysis, The solvers uses not Newton-Raphson method, which is nothing but applying the loads gradually actually. So the same formulation is used, but in the non-linear analysis, you cannot apply a lumped mass. You cannot apply an overall lumped mass throughout the problem. So you do that incrementally via Newton-Raphson method. So loads are applied incrementally. In a dynamic situation, a complex contact problems can be dealt with, or a high-speed dynamics event can also be solved. So dynamics problem requires a formulation F equals to ma, where F represents all the externally applied forces minus the internally applied forces. And m is the mass of the overall model. A is the acceleration. If the model is accelerating, then this formulation can be used. This is a basic governing differential equation in the dynamics. But this equation further needs to be integrated to obtain the time increment. So a very simple version is written here, but usually it is like that: x double dot applied forces. So this is a governing differential equation, which is actually needs to be solved in the case of a dynamic situation. For the dynamic situation, there are many examples, like a projectile impacting a plate or a ballistic material. So this is for example, a ballistic material. So a projectile is impacting this plate and moving out from this side. So this is a dynamic behavior. This movement of the projectile impacting and coming out from this side can be represented on a timeline. So if this is a timeline, these are the small events on this timeline. Movement of the projectile, getting impacted, perforated, and getting out from the other side. All these events are there on this timeline. So FEM solves this using a time increment. All the dynamics problems are solved using a time increment formulation. That means integrating the time with respect to a small time increment. This time increment that we have depends upon the element size. So as you can see that this is a contact problem, a non-linear contact problem, where this is a contact occurring. So this is a non-linear formulation, and the movement of this will represent a time, and time increment depends upon the size of the element. So in overall mesh of this, the smallest element will be taken as a reference element, and the time is the elastic wave that actually passes. So the wave mechanics also comes in the field of wave mechanics. If we have any element, then the deformation of this is a quadrilateral element. Deformation of this element depends upon the wave mechanics, and wave mechanics says that the amount of time required to pass, amount of time required for any kinetic wave to pass is depends upon the size of the element. So how and when this element will deform depend upon the small time, the size of the element that it has. So if we have a much smaller element, it will take more time to deform, and hence it will take more time to integrate these equations. These are the single equation for a single element. So there will be many equations for all these elements. They all are grouped together, combined together, and are solved in time. We can also see this during the hands-on. I will show you. This solution time of FEM depends upon the nodes and elements. As and when we increase the nodes and element, the accuracy increases, which is good for us. But correspondingly, it increases the solution time also. So if we have a limited resources, we have to manage between the number of elements and the solution time. And further, we have seen that the number of equations made is directly proportional to the degree of freedom. So as and when we increases the number of nodes, the number of degrees of freedoms increases and the solution time is further increased. So a engineer or a computer person actually, or the person who's doing the analysis, has to make a fine balance between the desired level of accuracy he needs and the element size he needs. Now, FEM as a solver, we have many FEM solvers available. We have ANSYS, we have Abacus CAE, we have Nastran, and there are various other software packages which are available to solve the FEM problems. Whatever we have, the basics that we have gone through for the statics and the dynamics, we'll see in the hands-on session also. So these solvers are used in automotive, aerospace, and industrial industries. And these products are very popular among the academicians and non-academicians both, because they are able to solve their problems onto this. Even the industrial people does not require a deep knowledge of finite element method, and they can use just as a modeling software, and you can use a basics and can solve their problems. However, the software package Abacus has the advantage that a user can define their own tailor-made materials. That means through the differential equations, we can actually put our own material. Like for example, in composites, the well-defined failure material is not available. So we can use our own well-defined or encrypted materials to use in that. Definitely for that, we have to write a small code. So that part can also be done in these FEM solvers. So it has majorly two major parts, which is first a pre-processing, in which we define the problem, what exactly problem we have. And how does we define the problem? We define the problem using, first of all, the deformable material we have. We have a deformable material or a rigid material. We will assign a property to that material, how much stiffness that material has, how it fails, which law it will follow to fail itself. We will assemble it if it is required. We will assign a solver to it. If it is a dynamic problem, we will assign a dynamic solver. Like I have told you that it requires a time increment and it needs an integration in the time domain. If it is a static solver, it will require a basic Newton-Raphson method to solve it. If there is some interaction, we will define the interaction this. Like for example, here you can see that these gears are getting meshed together and there is an interaction between them. So the contact mechanics will come here and will define the interaction. So for this, the contact mechanics is separately kept in a separate module. So if a user requires a contact mechanics, then he will have to study about the interaction. Then for all the problems, we require to put the boundary condition. So this is the essential step. Deformation, property assignment, assembly, and boundary condition. These are the essential steps required in every model. And then finally, we mesh the model. Now there is many meshing techniques are available, which makes the mesh very proper in your case. So if possible, and then the post-processing of the results are done using a simple output files. We'll see how that is done. So this is one basic hands-on problem, a very basic simply supported beam with a point load. Now the main aim here is to see how to define this problem in finite element software. We know that the central deflection of this simply supported beam is PL cube by 48 EI, where P is the load, L is the length, E is the modulus, and I is the moment of inertia. Now, since the beam is rectangular in nature, so moment of inertia is BD cube by 12. So if you put these values here and put the relative value, you'll get the displacement as 0.0152, something like that in mm. Now we'd like to see that can FEM produce this result. So quickly we'll see, because we have a shortage of time. So we'll see quickly in a simple hands-on if FEM is able to produce this result. So I'm using a software package Abacus. It's all this simple problem. As I said in these slides, that the first part is to define your model. It's a deformable model, so definitely my beam is deformable. So I will define it as a deformable. And let's make it 3D so that it is more visually acceptable. So this is a beam, a 3D deformable beam. Okay. And what is the dimensions of this beam? This is about 80 to 100 by 10. 100 by 10 is the 2D dimension. So we'll keep this as 100 by 10. This is 100. And the width is 10. The width of the beam is 40. In this side view, you can see. So the width is 40. This is a simple beam for us. Now we can produce. This looks a bit trapezium type, but this is not. This is due to the graphics issue, I think. Okay, so this is not like a trapezium. So what are the other things that is required? The other thing is property. So we have to put here which property it is. So for the deformation, we require only the Young's modulus and Poisson's ratio, because this is within the elastic region. So we'll define only these two. If the plastic region is also needs to be modeled, we need to see its permanent deformation or its failure. So elastic nature of this needs to be modeled along with the failure pattern. So we have in the elasticity, elastic model, isotropic. It needs to be seen that the material properties are in some units, and these are also in units. However, during defining the problem, we have not used any units because this is dimensionless. So whatever the dimensions we are assuming here, we will get the results in that also. So I have used mm. I have put 100 like that. So I've used mm. So I'll get the results in mm. Provided a condition, I will put the Young's modulus also in mm. So Young's modulus is 210,000 MPa. So MPa is Newton per mm square. So we can put it directly as 21,000. 210,000. Poisson's ratio as 0.3. And that's okay. So this will model the elastic part. If, for example, for the advanced users, if we want to model the plastic parts also, the plastic models are available to model various plastic deformations. And the failure of the models can also be modeled. So once this material is modeled, we will assign this material to this beam. Now, I was always in a fashion, I can kind of that why this assignment is required, why the assignment of the material is required. I mean, I have defined a properties, then it should take these properties. But the assignment is required because we may be having two different materials. So a software does not know which material to assign which properties. So that's why assignment of the material is important. The third step is assembly. Although it does not require any assembly, we just keep this in assembly mode. Then a step will define which kind of a solver I'm using. Since this is a static problem, so it will require a simple Newton-Raphson method to solve this. So a general static condition will be used to solve this. Interaction, it does not have any contact interactions, so we will not use this. Load is the boundary conditions. So my boundary conditions is that it is fixed from the two sides and the load is applied from the top. Fixed from these sides and load is applied from the top. Now to fix it from this side, I need one node here. So to determine the location, I will try to partition it. So I can crop this material or partition it. This is in dependent format. We can make it independent. So I can partition it. This face. So a simple line can be drawn, and then this can be offsetted. Add tool, offset. This entity needs to be offset. How much offset? 10. 10 from here, 10 from here. So let's offset 10. Here the offset feature is there. And then again we can define it for this one also. Feature, add offset. Offset distance is 10. So these are the two offsets we have. Now there is a load point also. So to define the load point, we need to give its, we can just define one line here so that the load can be applied on these particular nodes. So this is the location for the load line. So we can directly section it as a cell. So this is the part on which we can apply the load. Now before applying load, I would like to first of all curtail it, because this is a simply supported beam which is not allowed to move in the y direction. So we'll curtail it in the y direction. So for a simple supported beam, these two directions are curtailed. This, shift select this. These two directions are curtailed. U2 is not allowed to move down. So this is the boundary condition we have. The rest of the boundary condition is the load boundary condition. So you have to apply the load here. But the most important thing is to apply the load on the node. Since we have still not defined the mesh, first of all, we will define the mesh and then we will load it. Now to define a mesh, first of all, we have to discretize it. Discretize it, so we can have a discretization using a seed. So in this way, we have discretized it, and we can actually put the elements also on this edges. So this beam is uniform. So as and when the load is applied, uniformly all the points will move thoroughly. So we can actually put some elements here. Now the overall load to be applied here is about 1000. So we can put something around 50 elements here on this part. So one node will be here shared from here, and one node will be shared from both the sides. So we can put 49 elements in fact. So that will make 50 elements. Now element type, which type of elements is required? So for element type, it has a library of various elements. So for now, 3D stress quadrilateral elements are the best suited for such kind of a stress deformation problems. After that, we can actually mesh it. And a simple mesh is generated over this. Again, I'm saying that this looks like a trapezium, but this is a simple beam. You can see that it is a beam. So now these nodes which are here, they will be exposed to the loading conditions. So we will again go to the load module, and we will see that these were the nodes that are present here. So rather than that, we can select and make these nodes in a bunch or a group. We call that as a node set. Load node or load set. And we will select all these nodes. Selection is very important. Otherwise, the nodes will be this is my point which needs to be selected. Let's see. I will no. I have to select this. Node set. Let's see if it is. Yes, now it is selected properly.
Select the nodes based on the line.
Because my applied load is on the line only, on the surface. So what I will do, I will divide this load in all these nodes. As I said, I will apply the load proportionally, discretely. So I will divide this 1000 over these 50 elements. So when I apply a load from here, load, concentrated load onto these sets, then this direction is U2, and I will apply 1000 by 50. So this is 20 newtons on each and every node on this. I have to apply a negative sign to put it downwards.
The number is based on the number of nodes.
Number of which?
I mean, how you divide by the number of nodes.
I have first of all created 50 elements here.
Yeah, you already know there's a 50 elements.
No. I have generated 50 elements.
Okay.
During the mesh, I have written there 50 elements. Although I have written 49 because one end of the node is shared by this case. So one element is gone there. So 49 elements will be there. So overall on this will be 50 elements. So we have defined the load and mesh, everything is done. So let's see if we can get the results. If any error will be there, we will try to sort out that. If you can see in this message file, first equilibrium iteration for consecutive direction checks. So in all these cases, equilibrium equations are being solved. Sum of all the forces on the nodes equal to 0 in the x direction, y direction, z direction. So this is a deformation that we have got. And I don't know if you can indicate it. It's okay. So there is only one increment that we have defined, I think. We can increase the deformation increment in the step module. These modules are same in every software. So in the field variables, we need that this should be incremental. So we can actually make this incremental, even in space-time interval, maybe 10. So this will now change it to, the deformation will be in 10 increments. Again, this increment is the same time value that we have used and we have discussed that. Since the increment, we have increased the increment, it's taking more time to solve the same problem.
What could be force distribution inside the body in addition to the density of deformation?
I have given a force of 1000 Newton over the line on this. This is a side view.
What other places?
No, in a this is a simply supported beam. In a simply supported beam, I have used it like that only. I could have used the way you are seeing also. We could have distributed the load other side also. It depends upon the problem. In this problem, this is like this.
As a result of this force, as a result of this distributed force, there might be forces.
Yes,
Right?
yes, we will see that.
And it does give this distribution.
Yes, we will see the distribution. So as a result of this, you can see that due to the result of this, now the force distribution, obviously the stress of the force distribution is same. So the stress is force upon area only, per unit area. So you can see that the distribution of the stresses or forces as the bending is happening. Now the important thing that remains, that can we achieve this displacement or something very close to this? So let's see if that displacement can be achieved, is achieved. So first of all, we require a displacement. And this is in this direction, that means y. So we need to take u2 in account. And we can draw the graph also, we can prove the values directly. Prove values over the nodes. You can see this value here, u2. And you can see that it is changing. So this is my load point, 0.015, something very, very similar or very equal to what that bending cushion has arrived. We can draw the force graph also afterwards. You can draw various other field variables that are available. These are the default field variables. Like this is the yield point. This is the force. This is the strain. This is the plastic strain, but we have not used plastic strain. This is the equivalent plastic strain. This is the magnitude of the plastic strain. This is the reaction force, the stresses, displacement. So these are the default one that the software gives. We can choose our own. We can choose some extra also. If we are defining some non-linearity, we can choose that output variable also. So
In here, I think this one here is Euler-Bernoulli
beam. Yes.
I think this is like a deep beam. For deep beam, we have to use Timoshenko beam also. So I mean, 1/48 here is for Euler-Bernoulli.
Euler-Bernoulli beam.
So because the thickness of the beam here is the ratio with respect to 80 is deep beam. So we need to add also the shear deflection.
Shear effect.
So
shear effects from the Timoshenko beam can be added.
Then we need to add the Timoshenko.
Obviously.
So I think there is a very sharp finite element is a bit higher, 0.16. Here is 1.15.
Yes, these are there. But this is also important that the Timoshenko beam is considered for the large shear. The beam that has large shear effect. So that is accounted in the Timoshenko beam, in addition to the iron beam.
Yeah, this one here, what element do we use?
We have used a simple 3D elements, yes.
We use Maxat, right?
So these are the 3D brick elements, 8 nodes brick elements.
So it means that, brick element.
I've kept most of the things as default. You can change and reduce the elements, increase the elements. So for 2D, usually we used to check out the elements. Nowadays, in 3D stress analysis, we used to take the C3D8R elements only, the solid elements. So this is the basic introduction of FEM. In this way, this problem looks very simple. You have solved this problem using a simple equation, deflection equation, in a minute or so. But using FEM, it requires a time to solve this. But this is a simple problem that requires modeling. Otherwise, for the non-linear problems, for the contact problems, for the other higher order problems, FEM is a very specialized and important tool to solve and to give you an idea about the solution results. So this is what I have to show. I have tried to keep this presentation as simple as possible so that the graduation and the PG students should also be able to understand. If anybody wants to get the higher idea about the various modeling techniques defined in the nonlinear problem, we have a YouTube channel in which we define the coding behavior and modeling discussion of a complex fiber metal laminates, composites. The modeling of composites is very challenging in FEMs, and for the delamination problem also. So we have this, but this is for the advanced users. People can go there and check out the modeling ways. Apart from the modeling, many aspects of finite elements has been discussed in this video. So this is what we have. We have a time limitations. So thank you very much. If you have any questions from anywhere, you're free to
use for the fluid structure.
Sorry, fluid structure. Yes, people have used it.
Because this is related to the question raised before. In the fluid structure interaction, then we have two types of coordinates. One is for structure, which is, as you said before, it is, the type of the element distribution is just this type. But fluid is just like
in fluid,
yeah,
you're right.
Yeah. So then we have some kind of what you call it? should satisfy also the fluid problem, the structure and fluid problem. This one here is basing Abacus, right? Or
I have used one tool, yes, Abacus we have used. We can use any other tool also. ANSYS can also be used, or any other tools can be used. That's not the problem.
so the question is regarding that one, the moving coordinates, moving materials. Maybe need to what you call it? Need to explore more detail on it because it is totally different approach between the fluid and the
So I think you are talking about finite difference method.
no, because in the fluid usually we use finite for you. And for you. Here we use finite element and then we combine it. And then, so the problem is there. How to make it compatible. I never used about this before. But in ANSYS, there are some
Fluent, fluent. Through the fluent it works.
yeah. And there is also what we call it immerse finite element. That's also a different thing because immerse totally also different approach between the one that we discussed.
Anyone from the audience have any questions? Please, you are free to ask.
And that software handle the heat transfer equations.
Yes,
Yes.
the software actually has coupled heat transfer, thermal displacement solvers. So it requires particular solvers. As in, like he's saying that fluid solid interaction solver is there in that particular software. ANSYS has this. So in this way, this has a coupled temperature displacement. We have done that in our expressive videos. We've done that one temperature displacement analysis.
Can you export a couple with liquid? This one is couple thermal and
Electrical structural analysis.
electrical structure, but not fluid.
Not fluid. You can't see fluid here. Solvers are there. People have solved it.
Yes.
They have solved
They have
it.
in ANSYS, yes.
Nowadays, they have an a la carte package. You take a basic version. If you want for fluid, take another license. If you want to for the solid mechanics or solid interaction, take this package. Want some meshing improvements, take this package. So they have this a la carte package nowadays. Each and every license separately.
This one cannot do the, if the medium of the material is fluid, can model the equation, etc.
People have modeled it in YouTube. We have seen that people have modeled fluid solid interaction. But I have seen, and the way I have interacted with people, I have seen that ANSYS Fluent is mostly used to solve such type of problems.
Sir, I have a question on the rocket pattern. You told me that you used a composite plate, and above that you have a kind of rigid body, it is falling on the composite plate. So how many layers are used? So you're using stacking, right? Composite. So what kind of interaction you're using on that? And what kind of damage model you applied here?
Damage model of the composites?
What kind of damage model you applying and what kind of stack you are using?
Stacking.
Right? Stacking you using. So what kind of interaction you have between each and every cycle?
Okay.
That is random.
So in composites, what we have done, we have taken 6 layers, 8 layers, and we are using composites along with the metal layers, called as the fiber metal laminates, hybrid laminates. Composites with the fiber metal laminates. These are used in aircraft structures because composites are very brittle in nature. Once they are filled, catastrophe is zero. So metal layers are added in between so that even if it fails from the high, the material can have a ductile nature and can take the load. So in some cases, we have 6 layers, 8 layers, 5 layers are also there. In between them, we have put a cohesive elements. Cohesive elements are the elements that perform delamination between the two surfaces. So using a cohesive technology along with a general contact algorithm, you are saying that which is the contact that we have used. We've used a general contact, surface to surface contact, general surface to surface contact, where the one which has the higher stiffness is the master surface, but the one which has the lower stiffness is the slave surface. Because in contact mechanics, you have a master and a slave surface. So the one which has a higher stiffness has the master, and the one which has a lower has the contact. And after that, we have used a rigid impactor. So impactor is considered rigid. It is considered that we have not seen a deformation for the impactor. So it is made rigid, no deformable.
Problem with the composite is how to find the proper place with layers.
Yes.
Yeah, this one.
Yes.
How to find it?
How to find it? Yes. These properties through the experiments. Yes. So these are the energies. These properties are known as the energies, and these are known as the fracture energies. So amount of energy experienced during the mode 1. This is a mode 1 failure. For the fracture mechanics, it goes that this is a mode 1 failure, mode 2 failure, and mode 3 failure. So this failure is a mode 1 failure. So the amount of energy required to fail is the fracture energy. So we used to calculate the fracture energy for mode 1, mode 2, and mode 3. And we used to put that in the contact mechanics.
The question that Dr. Mahmoud asked before
Yes.
about the cells. Okay. I think here also that the cells, the size and the shape will change.
Formula.
Which one?
I mean, generally, in all cells here, the mesh formula. With the form, the shape will.
Yes, the shape will change. Yes, yes, yes.
And also the form changes. The size of the cell changes.
Size of the cell is changed. Yes. Size and shape will change as it will deform. Size and shape will change. It is saying that you can see that this is deformed excessively. Even there is, if I will apply a damage equation to it, damage formulation. There is a damage formulation known as by the name of Johnson and Cook. They have given a damage formulation. If I apply a damage formulation, this will make the material damage, and the damage will be seen by removing the element from the mesh. Element will be removed and it will show a damage behavior. We have many videos here to show the damage, like in this one, and see the damage behavior.
It goes to failure, right?
Yes.
Failure.
Yes, for the failure. So in this one, I have also used the damage equations from the Johnson-Cook model. So come on to the model. Yes. Now, as you can see that it is, so all the cells are getting deformed. And as and when the material's excessive limit is reached, then this is the failure. So this looks like that the material has failed, but what happens here is that the elements of these are actually being removed from the mesh, and they are not taken into the account during the calculation. To make this visually similar to the experiments, these elements are removed, so that now you can see that these elements are removed from the mesh. These elements here, these elements are being removed as and when they become, the plastic strain extretes, and as you can see, they are being deleted. They are being deleted. There is an experimental. That is what I have put in. Embedded in the code.
But you must see from the model of elasticity, you will understand that it has to fit at this form, no?
No. Modulus of elasticity works only till the elastic limit. After the elastic limit, plastic region starts, and then we have the ultimate strength. So the ultimate strength, the final strength, and the corresponding failure strength. These two are the important criteria. And there are various other damage models also. This depends upon the which type of damage model we are using. This is the ductile damage model that we have used. So this is what we have.
Have you recorded the
Yes. I think I have.
So you can send the link later.
Right. I think I have. Yes, recording.
Any other questions? Thank you very much.
Thank you very much for your time. Any questions from the audience?
Thank you.
I think.
Appreciate it.
Thank you very much. Yes. Some question is there from anyone?
No, thank you very much, Doctor, for the seminar. Thank you very much.
Thank you.
Yes.
Then stop the recording.